I guess we're coming up to 12:05. Any questions or issues for the good of the order before we get rolling? I guess from my perspective, you can still see the screen, right? My laptop, desktop. Yes. If you're shaking your head, I can't see because I've minimized your faces.
Yeah.
Can you see?
Yeah, we can
Yep.
see.
You can? Yes.
Yeah.
Yeah, great. I thought it'd be worthwhile just checking. I guess I won't do that. So the outlines that some of you uploaded, I commented on. The comments are very cursory. As I've said to you before, I'm really interested only in the final product, really. And but I use this as a method to get you going. And so some of you haven't. So you'll see a very terse comment from me saying outline ... question mark. And so it has no consequences, but think about that and get things in motion, because I guess in I think a week from this Sunday, then your PowerPoint will be due. I think that's what the deadline is. So that's one thing to keep in mind. What else was I going to do? Do I have this? Yeah, I was going to do this last. For those in class, you'd have seen this in my on my desktop and wondered what the hell it was. I guess if you didn't see my desktop online, you wouldn't have seen it, so you wouldn't have wondered. But today is my 40th anniversary of leaving my country and starting a job. I was your age, almost exactly, probably at that time. So you can work out what I am now. And it's relevant only because you might have realized that I'm not a native-born American. I think I grew up in the UK near London, and I left when I was 22. And in 1980, 81, Margaret Thatcher had just come into power. She's changing the financial system in the US. There's a small recession. There are no jobs in the UK. And so that's why I think it's relevant to you, because I think when you graduate from here, times may be tough, but they may also be an avalanche of activity that might happen. And so my path was to, and my message to you is to, if things aren't so favorable for jobs at this time, then think about going to graduate school. If you're an engineering student, as almost all of you are, you can probably get someone to pay for a master's degree by being a TA, depending on their admission times. And if that's not your idea of a good time, then get a job, but take anything that comes, go anywhere you need to go, and do what you need to do. I think I think you have to be a bit flexible in this time. I don't know what jobs are like, whether some of you started looking, but my journey was that I arrived in Vancouver, Canada on the 19th of February, 1981, ready to start a new job. I stayed with some friends, went to an NHL game with the Canucks and then must be Quebec City's Nordiques. I don't know if those teams still exist, do they? In those days, I don't think there were any hockey teams in Tampa or in San Diego and Vegas, etc. And they were all Canadian teams. And then took a Greyhound bus after staying with some friends on the Sunday, arrived Monday morning in Calgary, Western Canada. Started work that morning. Went out with my boss to get some warm weather clothing, as he said, and an alarm clock. And so after starting at 7 o'clock on the Monday, I left town at 3 o'clock that afternoon to fly to Edmonton, about 3 hours drive north. Stayed there overnight, and 4 o'clock in the morning, I got a plane to Norman Wells, Northwest Territories. And this wasn't that day, but this was the activity from that. And it was to work, actually, if you don't know where any of these places are, let's do this. There we go. Zoom out a little bit. So Norman Wells is right just below the Arctic Circle. And so you can see that the 60th parallel is it, top of the, or 39th? Yeah, top of provinces is 60th parallel. This is the 39th parallel at the bottom of the provinces, top of the states. So Norman Wells was where I was just then. So you get some, it's on a big river that flows, the Mackenzie River that flows into the Arctic Ocean. This is Norman Wells right here, I guess. And so I flew in there and started work at 8 o'clock on Tuesday. And we're standing on 3 feet of river ice in the middle of a kilometer-wide river and working. So that was my options. I remember when I was in the UK, I interviewed for some jobs. They were all overseas. One was in Australia. I decided I didn't want to do that. 2 were in South Africa, and I didn't want to do those either. I think one of my friends had a job in the Solomon Islands, Papua New Guinea, at a copper mine that I didn't want to do. And so this was the beginning of my North American journey, working on a drill rig with some drillers, a driller there. Driller sitting on a hot water tank, which we use as drilling fluid to keep warm. Less hospitable weather. Norman Wells across from the other side of this river, about a kilometer away. And Norman Wells is a oil town. It's an anticline, which is a trap for oil that exists quite shallow below the river. And so this particular job was to drill in the river as a site investigation for what would become, and I don't think you can see them there, but actually you can on the picture here, you can see here. So if we blow this up, I don't know if you how good it is to be able to see. If we blow this up, I don't see it actually. Perhaps it's on this. Let's see. Make it smaller. Looking for something very specific. Oh, there I am. This is Norman Wells. So here was the town. You fly into it only in the wintertime. The planes are split half 737s for cargo and half for people. And it was to do site investigation on these artificial islands. And so these are artificial islands which were built by dredging, I'm guessing, in the river. You can see some plant on there now. And what it was a very shallow anticline, a trap roil, directional drilling, horizontal drilling, what was in its infancy. So instead of drilling from the bank underneath the river and into the reservoir, they drilled directly down from these. So these are basically wellheads, these individual pads. And the site investigation was to do that. And so if you see these other pictures here, this one was, I think, later in the summer. Esso decided to go up there, and instead of a bunch of young guys and gal going, or gals perhaps, gal singular, I think, going up on scheduled flights. They rented a jet to fly up there, which was kind of fun. Bar open on the way home. I remember there's no bathroom on the jet except one of the seats which had a curtain to go around it. And I was reminded of this a bit about this time last year when I flew over Norman Wells on a flight to Seoul last January, I think, to see, actually you can see those islands there. This is in the wintertime. Obviously it's iced up. These are the drilling pads, if you can see them, linked with an ice road. You can drive across here in the wintertime. And the actual ice road goes to the west side of the Mackenzie and then to Alaska. It's called the Old Canal Road. And in the Second World War, when the Allies were worried about the Japanese coming up through the Aleutians, then this was a source of fuel for the war effort at that time. So anyway, so it may seem the ramblings of a demented fool, but my message to you is quite clear: is that things work out in the long term. So if you're having a hard time getting a job, I don't know what things are looking like right now economy-wise, but if you need to get a job, take whatever you can get, go wherever you need to go, and just do it, and things will work out just fine. I was going to send you this the other day, and then my computer crashed on me. But there is a job at DOE, specifically in the Geothermal Technologies Office. And I'm sure you can look for this online, but the Geothermal Technologies Office is hiring. It may be a bit above your pay grade right now. I certainly know these people who are involved in this at DOE. But hey, why not? If you don't ask, the more rejections you get from jobs, although it seems a bit dispiriting, actually the better off you are, because it means you're trying. And one of these days you're going to hit the the mother load and be able to get something. So if you're interested in this, look on the Geothermal Technologies Office at DOE, their homepage, and see if you can see what this is. It's to work at the National Renewable Energy Lab, NREL, which is in Golden, Colorado, which is a great building in a great location. And so there are jobs out there. And no doubt the $2.9 trillion that's about to be put into the economy, just like in 2008, when I guess you'd have been 10 or so, or the stimulus package generated a whole bunch of jobs as well at that particular time. And so I'm not presuming that it's doom and despair, but I think you've just got to take the opportunities that are open to you and go after them. So that's my message for the day. I was realizing that we haven't looked at videos in this class in a long time, and I thought we might just have a little bit of a diversion before we get going. So that's my comment for that. Anything else before we get going? Nope. We still only have one person here. They scared. I'm not sure what we did last time to scare you off. Anyway, all right. So I will get back into the scheme of things. I will put the stuff on the right-hand side. Well, just to summarize in terms of recapping what we did last time. And so I guess we made, without me scribbling some things, I'll go down through what I think are the main points, 3 main points. The first is that if you look at enthalpy, the 2 components being temperature and pressure that contribute to the energy that you can recover from a reservoir, by far the largest contributor is going to be temperature. And so that's why it's called geothermal energy, I guess, in that respect. So the pressure will get dropped as you recover stuff from it, but it'll stay dropped. And so you're not remaking energy from the pressure transition, but you are hoping to bring in temperature into the system. The second case, when we look at these kind of simple box models, these lump parameter models that describe the production of fluid from a reservoir. And of course, we need to know the production of fluid, because if we know the heat that's carried with that volume of fluid or mass of fluid, then we can calculate the potential energy that we recover. The behavior of that system is governed by this expression here, I guess, which is the important expression that we looked at yesterday. Oh, by the way, thank you, Andrew, for falling on the sword and using your computer so you couldn't take notes, if indeed people do take notes in these classes. And we made the case that the rate at which you can get drawdown of pressure in the reservoir is related to how quickly you take mass out of it, or volumetric flow rate, and the compressibility of the system, defined either in terms of volume or in terms of mass basis, given by these equations below, the compressibility of the aquifer or the compressibility of the fluid that's in the aquifer. And these define exactly the rates at which temperature will go down. It'll go down quickly if you produce it at a high rate, or if you have a low storage, because the right-hand side of this equation will be large, hence this. So that allows us to be able to say something about the pressure changes within a closed reservoir. And of course, the mass rate of flow that we're recovering from it, you can use, if you know the temperature, to calculate how much heat energy comes from it. And we talked about that. A more reasonable way to look at these lump parameter systems, though, is to take a box that, instead of having a closed boundary to it, with no flow across that boundary, is to have a box, but one which is resupplied by the surrounding material. And so this is alluded to in Justin's talk, where he looked at areas, part of the reservoir where you're producing, where you're drawing down pressure, and external areas to the side, where it's either being supplied by reinjection, potentially, or might be supplied by just natural resupply occurring into the system that comes from the flanks of the reservoir. And so if we do that, then if we allow for that resupply of fluid from the periphery of the reservoir, then what we can do is we can calculate the magnitudes of a couple of things. One, certainly if you keep on pumping from a closed system, the pressure ultimately goes to 0, because you'll completely deplete the system. If it's being resupplied from the side, it will reach some kind of equilibrium, where it will reach an equilibrium pressure, which is defined by the pressure drop from the original pressure, which is present at time 0, And that pressure drop is controlled by this parameter we don't really know, alpha. And there are two ordinates for that. It'll occur after a certain amount of time, traces, and that certain amount of time is equal to when T alpha and the storage is equal to about 1. It's actually about 3, not 1, but 1's not a bad number in terms of order of magnitude. And the magnitude of the pressure drop will be given by the mass rate of production, the time to that particular point, which would be this, right? This would be the appropriate time for that, and the storage in mass of the reservoir. And so we can calculate those. You can check whether these make sense. This has to be in units of pressure, right? Because it's equaling pressure drop. So if you take the units of mass rate of recovery, storage, and time, it turns out to be units of stress. And if you take the units of this has to be a non-dimensional parameter because it's equal to 1 on this scale. And so if this is equal to 1, then this is time, this is alpha, whatever units that is, and this is the storage in the system. So if you know the mass rate of removal from the system, then you can use that to calculate how much thermal energy is being removed. This is specific heat capacity, not compressibility. I'm sorry about the misuse of units. And all we have to do in this particular case is figure out what we'd use for alpha. And so one straightforward way of doing it would be to think of the outside resupply as being along a core, or as I mentioned last time, I think there could be more sophisticated ways we could do it with a flow net, for instance. We just realized that this rate here has to be equal to Q, which is a volumetric flow rate. So we could also use the fact that number of flow tubes over number of drops, hydraulic conductivity times change in head. We could convert the change in head to a change in pressure. We could convert the hydraulic conductivity to a permeability and get this volumetric flow rate from that, and it would be in terms of pressure. Actually, this pressure drop would cancel with this one on the bottom, and so we just end up with being able to define exactly what that is. Okay, so kind of a long recap, but those are the essential components of it. So we have steady state box models that we can allow for. What we haven't allowed for is the fact that when we looked initially at this behavior of injecting and recovering water from a reservoir, injection on the left, recovery from the right, that the pressure is not constant in space, but it changes. And so the expression that we might want to use is not one that has the reservoir represented by a box, where if we looked at across the reservoir, the pressure would be uniform. It wouldn't change with space. But in reality, the pressure will change as you go from injection, where you raise the pressure, to production, where you depress it, because that's what's going on. And so what we'll talk about today is two things. One is what happens when a gradient in space in pressure develops, as in a real case, around drawdown around a well, in terms of the flow rates that we might get. And we'll spend a bit of time on that, not too much, because I don't think it's particularly super important to the things that we might do in this class, but it's important to understand about it. And then secondly and thirdly, we'll talk about the rates at which we can recover fluid from the system and the likely temperatures at which they will be when we recover them. So those are our tasks for today. And I guess they're probably written up here, right, in terms of these would be this, I guess. Yeah. We only got through 2 the other day, but hopefully we can get through these today. So we'll spend a little bit of time on this, and by far the most important things are these 2 in the latter parts. And we'll finish that off today. This is probably the plan. Can you still hear me? You can in class, yes. I know. Good.
Yeah.
Good. It's actually better to be in a classroom with an audience, even of one, than being at home. Sometimes it's tough to keep your concentration and your voice up. So there's lots of math here. This comes directly out of Bixley's book, Grant and Bixley. So you can see that stuff there. And I'm not going to belabor the point, but I'm just going to talk about the general big picture issues. And the big picture issue is that if you have a reservoir where you start producing fluid out of a well, I guess it looks like a blunt object because I've enlarged it, then the initial pressure that you'd think would be uniform in the system, I guess would be uniform in the system with radius, will transform to be drawn down close to the well. And so this drawdown in pressure that you get here is a direct consequence of pumping fluid out of this. You can think of the flow regime as one, if you looked in plan view, it would look like a slice of cake. This would be what it would look like as you go away from the wellbore. So flow would occur in this direction here. The cross-sectional area has to go through here is much smaller than the cross-sectional area of here. And so if you write Darcy's law, just to make the point, with radius, then from continuity, the volume of fluid that goes across this cross-sectional area has to be the same as the volume of fluid that goes across this cross-sectional area at steady state. We're not in steady state. And so since this is a smaller area, the velocity here has to be larger. If the velocity here has to be larger, then the pressure gradient has to be larger. And so if you look at this behavior here, the pressure gradient is larger closer to the well, and it goes to zero at some infinite distance away from it. So that's just an explanation of the physical reality of it. We have talked about an expression which we've written in terms of hydraulic conductivities and heads as something like this. And in terms of permeabilities as this, where all that's changed is the variables, and this was some kind of compressibility and change in pressure with time, right? All we've done is we exchanged the dependent variables around. We wrote it really only for one-dimensional flow, but of course we could write it for flow in the horizontal, which is XY. And this would also be the same. And these equations govern transient flow that changes with space, so this gradient, and also in terms of depleting storage, this triangular area here is fluid that isn't desaturated, but it's where the pressure is dropped and it's supplied fluid by expansion of the fluid and compaction of the reservoir. That's basically what's going on. So it turns out that instead of writing this expression in 2 dimensions, where the 2 dimensions would be X and Y in the horizontal and Z in the vertical, in this particular case, we don't care about Z because we're in an aquifer which is confined between 2 impermeable boundaries. And so actually the gradient d2h dz squared is 0, so we just don't care about it. Instead of writing it in that way, we could write the expression in terms of pressures, in terms of radial coordinates. This isn't important. It's just that this is a substitution for this expression here. But you realize that instead of being written in terms of X and Y directions, the pressure is only going to vary in the radial distance. And so we only need to use one coordinate dimension to be able to define behavior. So the bottom line is that you can develop an expression that allows you to calculate that if you start producing fluid from this reservoir at some flow rate, so this would be in a volumetric flow rate, then you can calculate how the pressure would change as you go away from the well. And if you, for instance, drilled another well bore, I'm going to drill it here. Well, let's not do it there. Let's drill it closer to the well. If you drilled another well bore, then by measuring the pressure change in that second wellbore, you could use that pressure change versus time, or indeed you could use the pressure change within the wellbore you're pumping from. It's not very convenient to measure it there, but you could do. And you could use that to determine what these aquifer parameters are. And the parameters you want to define your aquifer would be what we've referred to, I guess we've called this as the specific, the volumetric storage. And you'd want to know what the permeability is of the system. And depending on the fluid you're pumping, you'd know the viscosity of that, because if you know your temperature of your water, you de facto know exactly what that is. So 10 to the minus 3 Pascal seconds at room temperature, and maybe 10 to the minus 4 at a couple of hundred centigrade, something like that. And so anyway, you could go through this long derivation, which I won't bore you with, but the bottom line is that you could make a plot for your own, for this red well that we just drew here. So you could make a plot for the change in pressure versus time. So the initial pressure would be P0. And at some later time, I know this is kind of a blunt instrument, the pressure would be some P, pressure P. That would be a particular instant in time, because of course, if you keep on pumping, the pressure profile will keep on going down, right? And so it would change to the next magnitude. So what you could do, imagine that you could take your pressure that you've measured and plot it relative to time in seconds on this figure. And so these would be your data. So at 100 seconds, the pressure is some magnitude. At 1,000 seconds, it's a different magnitude. At 10,000 seconds, etc. So a day is roughly 10 to the 5 seconds. I think 86,000 seconds per day. Another useful number if you don't have anything else useful to fill your mind. So these would represent the data on this plot here as a function of time. So you'd have that. So if you can solve this equation, this differential equation for the particular flow rates that you're pumping out of the reservoir, you get a solution for it. And it looks like in this. And if you plot that solution, it plots like this. It plots in terms of a so-called well function and a so-called, this is proportional to time. And you get a type, what's called a type curve. If you plot your data from the field in terms of the pressure at time 0 minus the pressure at any particular time, you get these different pressure change magnitudes, which represent your data. And so this is on log scale. And what this is suggesting is that as you pump for longer, the pressure drawdown becomes larger, right? Because this is increasing. So the pressure difference from the original is changing. So what you can do is you can superimpose these two curves on each other, which is really what's given on the right-hand side. The data curve are the one that I'm going to outline in red. And I guess the type, so-called type curve, if I can get blue, is the one given in blue. You get them so they exactly match. And then you take off the values for 1 over u. That's this pad. So we'll see if it keeps on going. I think it's probably fine. So you go up 1, and you go across 1. And you see that on your data, you have some magnitudes, which in this case are going to be what? These data suggest that that value is equal to a head change of 0.2. And I guess this would be at something like, there's 100 seconds, 1,000 seconds. This is, it changes non-linear, right? So this is 11, I don't know, it's probably 110 seconds. So you have the magnitude of time, which when 1 over u is equal to 1, and you have the value of h minus h0 when wu, this well function, is equal to 1. That's all you need. And so what you can do with these the so-called match points, the values of time and head drop, you can plug them into this equation. I make it larger, so that this expression here is equal to 1. Whatever the head drop you have, you've measured as the match point, you know what flow rate you're moving at, and this value here is equal to the hydraulic conductivity multiplied by the thickness of the aquifer, this value here. And so if you know what hydraulic conductivity is, you could calculate this. This is your one remaining thing, and you could convert that to a permeability if you so wished, right? Because we know this is the relationship that links permeability and hydraulic conductivity. This is hydraulic conductivity. So if you've measured, if you know the flow rate you're pumping at, you know what the match point where your hydraulic head or pressure has changed at a particular time, the time given by this match point, you can calculate hydraulic conductivity. You can use that hydraulic conductivity to calculate permeability if you wanted to. And secondly, you can use this magnitude of so-called transmissivity, which you've now calculated, to throw into this expression here. This value of u is also equal to 1. The radius is the radius where your well is. And so I didn't draw it on here, but the radius would be this distance here to the observation well. So you know that because you've drilled it and you know exactly where it is. So you have this. You know the time of your match point, which we said was 110 seconds or something, right? And you'd know the transmissivity for above. So you'd have everything you needed to calculate the so-called storage, which is equal to the specific storage multiplied by the thickness of the aquifer. So these happen to be done all in kind of groundwater units, but the groundwater units that we talked about in terms of hydraulic conductivity and transmissivities are related to permeabilities, given here. The heads, of course, are related to pressures, if you prefer to do things in terms of pressures. Volumetric flow rates are volumetric flow rates. And the storage magnitude are the same as the aquifer compressibility that we talked about. So this is not specific heat capacity, this is aquifer compressibility. So the units of this would have to be in units of 1 over stress, 1 over pascals. And so you should be able to check the dimensional consistency of that. So I'm not worried that you completely understand all the nuances of what we've talked about. It's just that there's a reality that if we pump fluid out of a reservoir, it doesn't necessarily behave like a box where all the fluid pressure changes everywhere are the same. They concentrate around the well. There's a cone of drawdown around the well in terms of pressures. If it's a so-called confined reservoir, meaning that the top and bottom of the reservoir don't allow flow to cross it. So that's the one requirement that allows us to work in this one-dimensional regime. Implicitly, we've worked with a radial flow field. There's only really one dimension in our problem because there's every single point we have in our aquifer is flowing parallel to itself towards the well. So that's why we lose the Z dimension in this. And so you get a drawdown. This drawdown isn't a drawdown that's dewatered, it's just dropped in pressure and it will release the fluid out of there. So there's still water that contains in here. I guess it could flash to steam, so it could change phase, but there's still something in there. There's still our liquid in there. And that we can calculate the rate at which we'd return fluid to the well based on that pressure drop. That's all I'm saying. And so you can do that evaluation. This is exactly the same evaluation that I talked about on the previous page in terms of the change in units. Both this well function and this U function have no units, they're dimensionless. And you can check whether these units make sense. Well, we can do it quickly, right? So the units of this, time is in seconds, permeability is in meters squared, viscosity is in pascal seconds, and 1 over r squared is this. Right? You know that I must have checked it beforehand. So it's 1 over pascals. It's exactly what compressibility is. So this one, if you do it, should be meters squared, pascal seconds, length. This is pascals. So this will cancel out with the pascals. Well, we can do it as well. Pascal seconds. Remember the adage, you can't tell whether it's right if the units are correct, but you can certainly tell if the equation's wrong if the units aren't correct. And so this would be in volume, so it'd be meters cubed per second for flow rates, and pressures would be pascals. So pascals cancel, seconds cancel, and meters, change this to meters squared, and that's indeed what that is. So anyway, you can make yourself a genius in this new job that you're going to apply for today by just being able to do simple things like that. Be able to check things and tell your boss that, no, that can't be right because the units don't match. And so anyway, you can make yourself valuable to someone. All right, so the first thing we said was that we talked in parts 1 and 2 before about the idea that we could have these box systems where pressures were uniform within the reservoir. They're not reality, but that's useful to us. If we look at drawdown around a well, item number 3, which we just looked at, we know that we could solve those systems to be able to get flow rates if we have a pressure drop between an injection location and the boundary of our reservoir. We could calculate what the flow rates would be that would be steady state in that particular case. That's what we've just done. So that's great, because when we want to calculate the heat supply out of a system, we've said that the rate of heat supply, I think I use H. So the heat rate that we can recover from the system is going to be equal to a mass flow rate times the specific heat capacity times a change in temperature. So this is a key requirement for us. This is mass flow rate, kilograms a second, joules per kilogram per degree centigrade, and degrees centigrade or Kelvin. And so the units of this will be joules per second. This is power by definition. And so if we pump a whole bunch of water, but it's cold, it does nothing for us. If we have no flow of water, but it's very hot, that does nothing for us. So we have to hit this sweet spot where we have both of these as being reasonably large quantities. So that's the issue that we have to deal with. So far, the only thing that we've addressed is that this can be large and we can calculate what it is. What about whether this is going to be large? And so now we'll turn our attention to talk about the idea of thermal breakthrough. And again, this is a concept that is important to understand the concepts rather than the math. We have no exams in this class, so we have no assignments that you're going to do apart from these reviewing of the stuff online. So absorb, if you like, the big picture of this, I think, and perhaps step back from the details of the math. Although you are engineers, and of course you should be able to calculate things. So let's go back to a one-dimensional reservoir. And so this is a one-dimensional reservoir, and I'm going to assume that the reservoir starts off at cold. So it's the obvious opposite of a geothermal reservoir, just because it's easier to draw the graph this way. What it would be, of course, is that the reservoir would start off at some temperature, which would be, I don't know, 200 degrees C. We'd inject water, which would be at 20 degrees C. And so the way we should draw it should be that we're injecting cold water into the reservoir, and the initial reservoir is hot. I haven't done that. I don't know why I didn't do it. I've done this, and this would probably represent, if you like, aquifer thermal storage, right? Thermal storage in an aquifer means that you inject water into the aquifer, which is hot. It comes from the summertime, from warming up and being used for cooling. And the aquifer originally is cooler, maybe 10 degrees. And so this is what that profile is showing. So let's do the inverse or reciprocal of a geothermal reservoir. Ignore what I've talked about in terms of this. And let's say that we start off at, let's do the opposite. I think I'm explaining too much. You guys are smart. So let's say we start off at 20 degrees centigrade and we're injecting at 200. It won't be 200, of course. So what would happen? Well, the whole of this reservoir and the whole of the water within the reservoir starts off at the cold temperature. As we start injecting the hot fluid, it will move through as a plug, like a piston. It will displace the fluid ahead of it that was originally cold and replace it with the hot fluid behind that front. And so all of the hot fluid will be displaced, if you like, as a piston. And so you could imagine this as giving just a cold front, a front that would go through this system. So it would be hot behind it and cold in front of it. But the other thing that's happening behind it is that all the components that make the solid reservoir, the sand grains, are going to be hot, and they'll be at the, or sorry, they'll be cold, right? They'll be at the original temperature of the water, which is in equilibrium with this. And so what will happen is that as you move fluid through here, the water will start off being hot, but the cold rock in the reservoir will cool it down, or the heat in the water will be sapped into the solid material to warm it up, and it will reach some equilibrium. Okay. So that's what we're looking at. So the net effect of this would be that in injecting hot water, we'd end up with a hot pulse of hot water, which would be tried to be cooled by the reservoir. And ahead of that front, the reservoir would be still its original temperature. So what we could do is we could think about an equilibrium condition. And the equilibrium condition was that we put in a certain amount of hot water into this upstream location. We could see at what proportion of the reservoir it would take for all of that heat to be dumped into the solid in the reservoir, which isn't moving. And if we did that, we'd find out that we would have kind of a, I guess I'm happier redrawing things. So you'd end up with a kind of a plug flow, which I've here, which would look like this. This would be temperature again. And so this part of the reservoir would be the same temperature as the injection fluid. This part would be the same temperature as the original aquifer. And what is happening here is that we're only injecting water at this higher temperature, but it's being used to heat up the reservoir rocks to the temperature of the fluid. So what we could do is we could calculate how far along this reservoir it would take so that all of the thermal energy out of the fluid being kept within the fluid and being dumped within the static reservoir, how far that front would be. And so that's the calculation we're going to do. And so the other physical system that's like is if you take filter paper, and you must have done this in high school. Filter paper, you take some dye in water, you put the filter paper within the dye, and you see that it rises up like a chromatographic column. Different dyes will go different rates depending on their convection rates. The point is that the rate at which the fluid is being sucked up in the capillary is different from the rate of progress of the chemical species that's in the chromatographic column. This here, the rate, the location of the front of where the fluid has gone, has gone much further than the rate at which the front of the thermal front has gone. And so it's that separation between the two that we can look at. And so this is basically the calculation. Imagine you have a reservoir that has a cross-sectional area of uppercase A. It has some porosity, which we've called theta as well as N. And so the volume that is open to flow of the fluid only is the product of A and the porosity. The part of the reservoir, if we could centrifuge it so it was completely solid with the solid grains, would be the cross-sectional area times 1 minus the porosity, because the porosity is the open part, right? Those are the proportions of the reservoir. And the fluid is only flowing within the voids of the reservoir, the porosity of the reservoir. And so the rate at which the fluid will flow is given by the volumetric flow rate. This is a velocity divided by A times, this is porosity, right? This is N in this. So if you're pushing a volumetric flow rate in to this cross-sectional area, if it's only able to flow within the portion of the area which is open to it, then the actual velocity of this is not going to be equal to Q over A. It's going to be equal to Q over A times the porosity. If there's no solid in this, of course, the volumetric, the flow velocity, this is equal to, if you like, the velocity. This is the volumetric flow rate over area. If it was completely open, then clearly the velocity of this would be equal to whatever the flow rate is divided by the area. But since only part of the area is open, it's going to be traveling much faster because this is always less than 1. Right? And so this is what Grant calls the chemical speed. It's really the speed of a molecule of water that is present at the front. If you wanted to know how far it's gone in a given time, you just multiply this velocity by time, and it will give you a length, and that will be how far that molecule of water will travel. So there'll be a chemical front. So this here is what we would call front. If you like, the chemical speed will be equal to the velocity chemical times, no, didn't want to say the chemical speed, the chemical travel distance. So this length here, I'm going to do a bad job of explaining this. Is going to be V chemical times time, right? So you inject it at time 0, you wait 10 minutes, 10 seconds, if we're doing SI, you multiply this time by the chemical speed, which we've calculated from this, that's how far it's gone. It's going to have traveled much further than if it was just an open cross-section, because this parameter might be 0.1, 10%. And so then it'll travel 10 times faster than the volumetric flow rate would have suggested it. So that's one point. The thermal speed, rather than the chemical speed, is the velocity that this front is traveling with. So this front is moving at V chem. This front is moving at V therm. And the thermal speed is the rate at which a front will move that's taken all of the thermal energy that's been in the water that's injected so far in time, and it's distributed that amount both within the water and within the solid, but kept it at the injection temperature. So clearly, if it's doing that, then it won't have traveled the same distance that the physical molecules of that, because we want it to be at the same temperature it's injected, but it's spreading that temperature, thermal energy, both between the fluid and the solid. And so what we can do is a very simple thermal balance, and it's given by this below. So the amount of heat you inject in the fluid is going to be given by specific heat capacity of the fluid, the density of the fluid, and the volumetric flow rate of the fluid. Meters cubed per second. The temperature differential between the reservoir and that fluid, and for how long you inject it, multiplied by time, really, not delta time. So this will be in joules. It won't be power. It'll actually be in joules, right? Because it's this term will be in joules per second multiplied by seconds. And so this will be the amount of energy injected, right? So it's the same as the amount of energy in a bathtub of a given volume. The volume that's injected, so Q times dt. This is exactly the same as what we'd have called volume, right, before, so uppercase V. Meters cubed per second times seconds. That's the volume that's gone into the system. So the volume that's injected multiplied by density, specific heat capacity, and time change gives you what we know of as, we've called it U before, right? We haven't called it U. So in other words, density times heat capacity times volume times the change in temperature is equal to energy. That's all this expression is. So this is the energy we've injected within the water, the thermal energy. This is also the thermal energy, but this is how much energy has to be absorbed from the reservoir. And so the reservoir has a volume of the reservoir. It has, has a density of the reservoir, the specific heat capacity of the reservoir, the temperature that we want to raise the reservoir to. So in this case, it's going to be 200 degrees C or whatever we want to. I guess 200 centigrade minus 20. The thermal velocity of flow multiplied by the area of the reservoir, the total cross-sectional area of this reservoir, and the time. And so we know that that temperature that we want has to be the same. It's coming in at 200 degrees centigrade. We want not just the water to be 200 degrees centigrade, but we want the reservoir and the water to be 200 degrees centigrade. So clearly, the distance that front has gone is less than the molecular distance it's traveling. So bottom line is that we can equate these two to each other. If we equate them to each other, we get this expression here. And this expression contains two parameters. It contains a chemical velocity here, and it contains a thermal velocity. And these are the two things that we said that were the velocities of these two fronts. And we can rearrange this equation to get the ratio of those two velocities. And if we do that, we end up with this expression here. Very simple expression. And that's all that matters in this discussion. The rest, I think you just need to physically understand what it means. It means that the ratio of these two velocities, how far these two fronts have traveled in a given time, is given by the porosity, the density of water, specific heat capacity of water, divided by porosity, density, and specific heat capacity, if you want, these are of the water, just to make that clear. And 1 minus the porosity of the density and specific heat capacity of the material, quartz. So this would be quartz, the reservoir rock. And you can rearrange this and resimplify it. And if you do that, you end up with this expression here in the ratio of the specific heat capacities and densities of the reservoir, the medium, and the specific heat capacities and density of the water and the porosity. And this is 1. It's bad looking 1. And this is 1 over. And all this says is that if you look at, if I go back to this diagram, maybe by making it smaller, because I see some people are still scribbling down some things, is that the front of the water that you've injected, the molecule of water that you've injected at time 0, is ahead of the front of the heat. And everything behind here, the reservoir and the water are at the same equilibrium high temperature. Everything ahead of this blue part, the reservoir temperature is cold and the water is cold. And in this part, the reservoir temperature is getting warmer and the water temperature is getting cooler. So this is a transitional area. But the two fronts we're talking about are, this is the thermal front and this is the chemical front that we talked about, and they're separated. And so they vary depending on the porosity of the reservoir. If the porosity of the reservoir is 100%, there's no physical material in the reservoir at all, it's like flowing in a pipe, then there is no separation between these. They're one and the same. If the porosity is if the porosity decreases, so the pore space that the fluid flows in is only 30% of the cross-sectional area, then they're separated by a factor of 2 for this value here, which is equal to about a half. If it's 10%, so these are all reasonable numbers for reservoirs, between 10 and 30%. The difference between the molecule of water is 5 times as far ahead of the front of the heat in the reservoir. So that's really what we're saying. And actually, if you throw 0 porosity into here, then this becomes infinity. So it means the molecule of water would go infinitely far because the porosity is so small it's being squeezed, and the distance of the thermal front would go no distance at all. So don't worry about the math, but think about the physical concept of what this means. It means that the aquifer or reservoir is originally at an ambient temperature and the water in it is at that same temperature. You inject water into that for re-injection at a different temperature, and that temperature means that it will want to put that heat or cold into the reservoir, and so it will change the temperature of the reservoir at the injection point, which is what we're talking about here. Somewhere downstream, where you're taking fluid out to be able to produce energy, this will already be hot water ahead of this, right? In our thought of what a geothermal reservoir would be. And so there's no temperature change in this. But the thermal front influences the distribution of temperatures in the reservoir. So our idea is one of a box where the pressure is uniform is not really real. And our idea 2 of a box where the temperature might be uniform is not really real either. And so we'd expect to see these kinds of behaviors that we alluded to in the very first moments of this topic. And that is that the pressure will change as you go from injection to recovery, and the temperature will change as you go from injection to recovery. If you inject really quickly, then you don't really want this front to make its way all the way through to this point here, because you'll be producing cold fluid. And so that's the reason why we care about this. We want the residence time of the fluid within the reservoir that's re-injected to be long enough that it picks up heat either from conduction from below the reservoir, this will be conduction from below, or resupply of heat somehow within the reservoir. We want that to be able to happen. So we don't want this front to be able to advance all the way through the reservoir, so it kills our production. Because we know that if we produce here at a big mass flow rate, and whatever the specific heat capacity is, but the temperature is no good, then we don't have a viable geothermal system. So that's really the point of talking about what we talked about. So I think it's kind of neat. It's not a straightforward concept to understand, but that's it. And maybe I should have drawn my diagram that we're injecting cold fluid, which is really what the reason for this is. So the way we've done this here with injecting warm fluid, as I say, is much more indicative of aquifer thermal storage, where you put hot water into a cold aquifer. You do that in the summertime, and then in the wintertime, you withdraw the heated water from the wellbore, and you want to recover that heat and use it to heat your home. It's the basics of aquifer thermal storage, which now is back in vogue. So that's a bit mathematical and more than really what I wanted to do, but it does relate to the fifth and final question. So the first one is, what are the rates at which thermal breakthrough will occur within the reservoir? Well, we can calculate that because we know how quickly the fluid will go from inlet to outlet. And if we look at these ratios of velocities, we can calculate that it's going to take, once breakthrough has occurred of the injected fluid, if we wait 5 times longer, then that's when the cold or hot front will break through to the production. So we can calculate that. But the other question is we've made an assumption here. And we've made an assumption that all the hot water that gets injected in here, we can calculate exactly how far that front will go based on that water giving up all its heat to the cold aquifer. So that's an equilibrium situation. But it may be that it takes time for that to occur. So for instance, if we pushed water very quickly through this reservoir, we'd expect almost no heat exchange to occur. It wouldn't be at thermal equilibrium. And so another question we might ask ourselves that's different from this equilibrium condition is, how quickly can we inject fluid through our reservoir? Come back to this figure at the top. How quickly can we inject fluid into our reservoir so that this front stays in one place and doesn't get washed through our system? Because now we can look at some different assumptions. So again, the physical system is one where we don't assume that there's some thermal equilibrium in space. And I'll avoid this figure above. It's basically this idea here. I think this is wrong. This should be infinity. Actually, I was just looking at the notes before. And this is the idea. And so say you have an aquifer that has a lot of grains in it, and the grains are tiny. So when you inject water into these grains, if they're really small, in the limit, if they're dust, then all the thermal energy that's present in these grains will be distributed between the water and the rock, which will be at the same temperature. But if these grains happen to be really big, say the size of baseballs or basketballs, I guess, which would be more reasonable, it would more closely represent our rock. So the basketball would be the size of these individual blocks. And in an EGS reservoir, as I guess I've got the picture here. In an EGS reservoir such as this, where we're injecting cold water, wanting it to heat up, this one. We're injecting cold water, we're wanting to heat up in this geological heat exchanger and then come out as hot water. This is the region that is these basketball-sized blocks of rock. And so the rate at which we can remove heat from these basketball-sized pieces of rock is not infinitely quickly. And so we can look at 2 different regimes. The first regime would be the one that we've just talked about when we talked about this equilibrium condition. And that is that we inject water here. The water that we inject into a hot aquifer immediately becomes the temperature of the reservoir. Immediately becomes the injection of the injection temperature. And in other words, all of the heat energy that pre-existed within the reservoir, which was injected in here, is carried downstream to the production well. Right? And so the thought is that if the reservoir instantly gives up all its thermal energy to the cold water that's flowing past it, then this portion of the reservoir will be chilled by the injection fluid, but the water will be warmed, and the water will be carried downstream, so that where you produce the water downstream, it will actually be hot, the same temperature as the reservoir. As you keep on injecting, slowly each slice of the reservoir will be chilled. Actually, it's this same thing as this thermal front moving through the system. This portion of the reservoir will give up its heat energy, which is the area under this curve, and send it downstream. And so the cold front will move through the reservoir. And suddenly, when it gets to the production well, all of a sudden, the temperature will drop. So if you look at the recovery temperature from the reservoir, initially, as you recover it, it will all come out at the temperature of the reservoir. When you get breakthrough to this point, in other words, this slice moving along, all of a sudden the temperature will go down to your injection temperature, and you'll be producing fluid at the injection temperature because you've taken all the heat energy out of your idealized reservoir. That's the best condition you could have. It means that throughout the operating lifetime of your reservoir, you're producing hot water. This is 30 years. And then when you finally get breakthrough to the production well, it's cold, but you don't care because you're going to go away and you'll drill a well somewhere else. And you've paid off your well and everything's fine. If instead of being very fine-grained powder, the reservoir happens to be basketballs, then the rate at which you can supply heat from these basketballs to the water that's flowing around them is tiny. It's got very little surface area. So what you'll do is you'll inject water at an injection temperature. It'll go across your reservoir and it will gain a little bit of heat, but it'll come out the other side, and at the other downstream end, it will still be cold. And so the trajectory for this behavior, where you have big blocks, is going to be something like this. Your early temperature recovery is going to be mediocre or bad, and it will draw down over time, but it's never been good, so it might not be viable. So one of the key issues in geothermal reservoirs, and EGS reservoirs in particular, is how do you get enough surface area in the reservoir to be able to get enough heat out of it to make the heat rate high enough that it becomes viable. So you get this kind of breakthrough here instead of the blue one. And so the ideal case is a reservoir that has lots of surface area. So you quench the reservoir at the well bore, and that front slowly moves through, so the cold front finally gets to the production well 30 years later. The difficulty in this is that sometimes a high heat surface area means finely grained material, which potentially has a low permeability. So when you're looking at this equation that we've talked about, the energy rate is equal to the mass flow rate, specific heat capacity, and delta T. You might be producing at high temperature, but if the flow rate is terrible, then you don't have any power coming out of your system. And so that's the dilemma in a nutshell in all of these, the key issue in EGS geothermal systems and other hydrothermal systems as well. You have to have a flow rate that's high, and you have to maintain the temperature that you're producing fluid at. And you can only keep the flow rate high if you re-inject your fluid to replenish the reservoir, or indeed this is the source of your water for an EGS reservoir. And if you're not careful in terms of your management or your conditions of your reservoir, then your production temperatures are going to be cold. And I thought I'd get through this. Here you can see basically the idea, and you can probably relate to this more in terms of these figures. So think of pushing water through a fracture. If you push water through the fracture really quickly at a high flow rate, you won't pick up much heat because it has no residence time in the fracture, and it's controlled by the conductivity of the rock in getting from the rock into the fracture. If you have flow that occurs very slowly on the fracture, then the residence time of a packet of fluid in the water is there for a long time. So it has a long time for the temperature to conduct into that fracture. And so this will gather more heat energy, but the problem is low flow rate times high temperature really doesn't necessarily give you much power, because it might be at a higher temperature, but its flow rate is horrible. And so this is the dilemma of all of these systems. So you can look at water outlet temperatures. This is for a single fracture that's flowing at some given flow rate. If you have a single fracture, then you don't get much temperature out of it after some time. This is in years. If instead you break this up into multiple thin fractures with a very small spacing between them, then the temperature that you get starts off high and stays high longer. And the more fractures you have and the shorter spacing between the fractures, the longer you can keep that temperature high. So this is in years. If you can keep it high for 100 years and still get a big flow rate out of the system, then you have a potential to have a viable reservoir. And I guess that's really, and actually, why don't we finish with this? So if you look at some of the historic results, so you'll recognize this figure here is kind of the corollary of this figure here. If you have a good reservoir, cold water works its way through to the production at 30 years and then it dies off, as opposed to having a mediocre reservoir, which is always cool. This is in terms of log time, but these represent two reservoirs. Fenton Hill, which is in New Mexico, which is the very first EGS reservoir, starting in the 70s. The UK scheme, Rosemanose, which was in the 1980s. I know, before you were born, both of them. But if you look at the data for those reservoirs, these are the data. So this is temperature of the recovered fluid versus time. And they kind of a little bit conform to this. It was over a very short period. It was over production phase to look at experimental of what the productivity of this reservoir would be. So these are not 30 years, but these are 6 months, say. But you see this general behavior that you start off high and your reservoir slowly diminishes in quality as you draw down between the reservoir temperature and the injection temperature. This is this normalized temperature. And if you look at different models to represent the behavior, these are actually the data. The data are the same in both of these cases, but you see it's conforming to the kind of behavior that you want, which is a step function, rather than the behavior which you might get, which is this kind of blue dotted line, which would be equivalent to this, but it's in log time on this curve, not natural time. So that's it. We're right on the money. Any questions? I guess it took longer than I thought. I plan to start talking about chemistry on week 7. So we're a week behind, but we don't need all the time we had allotted for drilling and surveying, I don't think. So I think we're in good shape.